Hello everyone, my name is Jonathan Alcarai, and I would like to welcome you all to my explanation of what combinatronics is. Generally speaking, combinatronics is the branch of mathematics that studies the number of possible combinations of a certain phenomenon. For example, we are at a restaurant and the menu has 4 appetizers, 2 pasta dishes, 3 fish dishes, and 2 desserts. So, how many different combinations of meals can one have, considering that one dish from every course is mandatory? The answer is actually quite simple. To get the desired number of combinations, we must multiply the 4 appetizers, the 2 pasta dishes, the 3 fish dishes, and the 2 desserts, which gives us 48 combinations. Quite easy, don't you say? Let me show you another example. A band is formed by 4 members, A, B, C, and D, and each of them plays a different musical instrument. Considering that A knows how to play B's instrument and vice versa, and that C knows how to play D's instrument and vice versa, in how many different combinations can the band play in? The answer is factorial 2 multiplied by factorial 2, which gives us 4. And this is because the band members can't play both instruments at once. Now let's tackle a much more intriguing and famous example, the Enigma machine. The Enigma machine is an electromechanical device used by the Germans in World War II with an electric signal passed through wires and various mechanical parts. The easiest way to explain the mechanics is to follow the journey of a single letter from keyboard to lampboard. So let's delve deeper into the device that played a fundamental role in the Second World War. When the operator presses a letter on the keyboard, it creates an electric signal that begins the journey through the Enigma machine wiring, that will end with a lamp flashing on the lamp board. The first stop on the journey is the plug board. Here the signal is connected to the letter input on the plug board. Some of the letters on the plug board will be wired up to other letters, the plugs, causing the signal to be diverted to a new path. The next stop is the static rotor, which, as the name suggests, does nothing to the signal. It simply turns wires into contacts, which will lead our letter to our next stop, the rotors. I'm sure that until now you were thinking, well, maybe this isn't so difficult after all, but this is where things start to get complicated. So, to give you a general view, there are 3 rotor positions, right, middle, and left, each passing an electric signal to the next. To make things tricky, as each letter is entered, the rotors rotate by 1 position, so that the same letters are never connected together in the same message. So, after the rotors, the letter gets to the reflector, which takes the input and reflects back the electrical signal for its return journey through the rotors. Keep in mind that even on the return journey from the reflector, the letter becomes even more encrypted as it passes through the rotors once again. The final stop is the lamp board, where the plug board output is connected to the corresponding lamp for that letter. To clarify any doubts on the structure of the Enigma machine, I'll put up a picture on the screen for a few seconds. But in the end, how effective is the Enigma machine at encoding letters? Let's find out, using 4 steps. To start, we know that the 3 rotors with 26 letters each give us 26 to the power of 3, which is equal to 17,576 encipherings. This is given by the fact that all the letters in the rotors can be repeated. In the second step, we see that the positions of the 3 rotors can be exchanged. So we have an additional factorial 3 equals 6 combinations. In this case, the 3 rotors obviously can be used more than once in a combination, and that is why we use a factorial number. In the third step, we see that the number of possible combinations of pairings of G couples of letters of an alphabet of n letters is given by. In this case, n equals 26 as the letters of the alphabet, and G equals 6, as in the possible combinations of the rotor, as seen before, factorial 3, which gives us 6. So we end up with. You might be asking yourself why the value g was also multiplied by 2 in the formula, and the answer is quite simple. As we said before, on the reverse journey, the letter is encrypted for a second time. Thus, we must consider twice the factorial value of the rotor's position. So, the number of possible keys is given by the fourth step, which consists in the multiplication of all previously found values, which were 6 times 17,576 times 100,391,791,500, which is more than 10 millions of billions of combinations. This extremely long number was, however, not enough to guarantee the success of the Enigma machine. Now you try. Can you manage to enigmatize the word computer? Keep in mind that the word has 8 different letters and that they cannot repeat themselves in one combination. If you feel as though you have quite a good grasp on combinatronics, you can even try to anagrammatize the word school. You may be thinking that it's the same thing as for the word computer, but think again, because not all of the letters are different. Remember to submit your answer to the comment section. I hope this video was helpful and thanks for stopping by. See you in the next one.